do an example now of finding an orientation on a surface. Right? So here we want to find the upward pointing orientation on the surface, which is the graph of f equals x squared plus y squared, which of course is just a paraboloid, over the disk of radius 3. Right? So imagine that disk of radius 3 in the xy plane, and we just want the piece of the paraboloid that sits over that. Right? That's the surface, and we want to give it this upward pointing orientation. So the first thing we need to do is parameterize the surface. Right? So we have a bunch of x squared plus y squareds here, so that suggests using cylindrical coordinates. Right? So cylindrical, right? So here, x is r cosine theta, y is r sine theta, and z, well, on this surface, z is f here, so z is x squared plus y squared, and so that means z is just r squared. Right? And now what about the domain? Well, we need some restrictions on r and some on theta. Right? So since we're interested in this over this disk of radius 3 here, that means r is going to go from 0 to 3. And since we have the whole disk, theta is going to go from 0 to 2 pi. Right? So this gives us our parameterization. R of r theta is r cosine theta, r sine theta, and r squared. Right? So as usual now, we need to compute the derivatives. So the partial with respect to r is cosine theta, sine theta, 2r, and the partial with respect to theta is minus r sine theta, r cosine theta, and 0. All right. And then now we have to decide on an order for the cross product. We have to figure out which is the right one. Now, you could do some tricks with thinking about the grid lines on the surface that are given to you by taking lines where r is a constant and theta is a constant and graphing them here. Or what I think is kind of, to me, the easiest way to do this is to just pick an order, do the cross product. Right? Because worst case scenario, you pick the wrong one, but there's only 2 choices. So if you pick the wrong one, just multiply it by -1, and you got the right one. All right, so let's go ahead and do that. So let's say r theta cross. So let's say here we try r theta cross r. Right, so that gives us minus r sine theta, r cosine theta, 0, and then cosine theta, sine theta, 2r, I, j, and k. All right, so if we compute this cross product, we get 2r squared cosine theta minus 0. 2r squared sine theta, and if we do this, we just get minus r. Okay, ran out of room on the edge there. Let me go ahead and write this on the next line. So that was 2r squared cosine theta 2r squared sine theta and minus r. Okay? All right. So we have to ask now, is that the upward pointing one? Well, there's 2 ways you can see this. notice here the k component, which is in the z direction, is negative. So that means the z component, or the k component's always pointing downward, and so that's the downward pointing one. But sometimes it might be a little hard to tell, you know, if it's the right one that we wanted, especially when we're talking about, you know, when we're trying to find, say, the positive orientation on a closed surface. So while, you know, here we could be done by observing that, oh, okay, that the k component's negative, so it's pointing down, which is the opposite of what we want. Let me show you another way we can do this. So, and this will kind of work when we're talking about closed surfaces too, which is a little bit more ambiguous. You can't base it just off that as readily. Okay, so let's sketch the surface. Right? It's just a paraboloid. Right? Let's put one of these on here to denote some thickness. Right? And then x is going this way, y this way, and z is going up. Right? So it's not so important that we get a very precise sketch here. But what we can do is we test this vector field at a point. Right? So test r theta cross r at some point. Right? Now, something to keep in mind here is when r equals 0, we kind of have like a bad point in some sense, right? Because when r is 0, it doesn't matter what theta is, we always get the same point. So somehow that bottom vertex of the paraboloid here is bad in this parameterization. So let's just pick something that's not that point. Right? By the way, also you can see if you pick r equals 0, we just get the 0 vector. All right, so there are some technical issues with that, but we'll kind of brush over them. Anyway, so let's pick a test point. Let's say, let's test r theta equals, let's use r equals 1 because that's nice. And we can use theta equals 0. There's no big deal there. Right? So where is that point on the surface here? Well, it's at theta equals 0, so it's somewhere above the x-axis, and it's at a radius of 1. So it's somewhere above this point, which let's say is right about here. All right? Let's make that really big and visible. All right, so if we plug that in, so if we do r theta cross r of 1, 0, we can test that, and, well, 2r squared cosine theta is just 2. Okay? Plug here, we just get 0, and plug it into the z component, and we get minus 1. So at the point 1, 0, the vector field is 2, 0, negative 1. So what does that look like? Well, there's nothing in the y component, so it lies in this kind of xz plane here, and it goes out 2 and down 1. So we get a vector like that. All right? So that we can see from there, all right, that's actually pointing outward from, or downward from the paraboloid. Right? So this is not the one we wanted. Okay? So this is the incorrect one. But that just means we wanted RR cross R theta, and we fixed that by just putting a minus. So we need RR cross R theta, which is negative R theta cross R, R. And so we just negative all this stuff. Minus 2R squared cosine theta, minus 2R squared sine theta. Right? But we're not quite done yet because an orientation is a unit normal vector field. So we just have to take this thing, find the magnitude, and divide. So the magnitude of this guy of RR cross R theta. This is, so if we square both of these and add them together, oops, why am I putting a vector there? This shouldn't be here. Meant to draw square root. Right, so we have 4 r to the 4th cosine squared theta plus 4 r to the 4th sine squared theta, right? Sine squared theta, right, plus r squared. Right, so this is just square root of 4 r to the 4th plus r squared. Right? You could simplify that a bit to r times the square root of 4r squared plus 1, but there's not much point. Actually, there is. We can cancel some r's here, so 4r squared plus 1. Right? So then, the orientation is, call it n, which will be r cross r theta over the magnitude of this. Right? This will just be, well, the r will cancel one r from each of these. So we get minus 2r cosine theta minus 2r sine theta 1 over square root 4r squared plus 1. Right, so again, this r right here cancels 1 from each of those components. So this here is the unit normal vector field that we wanted. Right? It points upward, and it's unit normal, so that's the upward pointing orientation of this surface. Right? I hope that made sense, and see you in the next video.